In this lesson, we'll be looking at electrical and electronic circuits. First, let's look at amplifier circuits. Here we have a common emitter amplifier. It's called common emitter because the emitter lead is grounded to AC through C3. It is AC coupled through the input and the output. It is most commonly used as a microphone preamp or a headphone or speaker amplifier. Resistors R1 and R2 provide the bias voltage to the transistor base. The gain of the amplifier is approximately the value of R4 divided by R3. We say that R3 provides degenerative feedback because as the current through the emitter increases, the voltage across R3 increases. This reduces the base to emitter voltage, which tends to reduce the current through the emitter. In other words, the circuit is stable. Here is a common base amplifier. The base is AC grounded through C3. This circuit has a low input impedance and a high output impedance. R3 has a fairly low value and R4 is much higher. Receiver preamplifiers are a likely place to find these circuits. This is a common collector amplifier. Capacitor C2 provides a low impedance path to ground. This circuit is commonly called an emitter follower. That means that the voltage output will be about the same as the voltage at the input, but with low input impedance and high output impedance. The common collector amplifier has blocking capacitors on the input and the output. The emitter load resistor R3 provides bias stabilization, meaning that this circuit is less likely to oscillate. Vacuum tubes came along before transistors, so you can find vacuum tubes being used as common cathode, common grid, and common anode amplifiers as well. You find grounded grid amplifiers being commonly used in linear amplifiers. They can handle 50 ohm impedances and they are not prone to oscillation. Operational amplifiers, op-amps, are a favorite of mine. They provide very high gain based on a small voltage between the positive and negative input leads. If you apply the input signal to the positive input lead, the large output signal will be in phase, that is, not inverted, compared to the small input signal. If the input signal is applied to the negative lead, the output will be inverted, that is, it will be 180 degrees out of phase. Op-amps make great differential amplifiers. That means that the output will be an amplified version of the difference in voltage between the two input leads. Op-amps can provide a lot of gain. However, as frequency increases, there comes a point where the circuit gain begins to fall off, that is, attenuate. This is the point where the open and closed loop gains converge. For a simple op-amp inverter, the gain of the op-amp is the ratio of the feedback resistor R sub F divided by the value of the input resistor. From the previous slide, what is the voltage gain if R1 equals 1800 ohms and R sub F equals 68K ohms? Well, the gain equals minus R sub F over R1, which is equal to 68,000 divided by 1800, which is a gain of approximately 38. From the previous slide, what is the voltage gain if R1 is 10 ohms and the feedback resistor is 470 ohms? Well, 470 divided by 10 gives you a gain of 47. From the previous slide, what is the voltage gain if R1 equals 3300 ohms and R sub F equals 47K ohms? the gain will be 47K divided by 3.3K, which is a gain of 14. What is the output voltage if R1 equals 1 k ohm and RF equals 10 k ohms and the input voltage is 0.23 volts? Well, the gain is going to be minus R sub F divided by R1, which equals 10,000 divided by 1,000, which is minus 10. The output voltage is going to be the input voltage times the gain. So we have an input voltage of 0.23 multiplied by a gain of minus 10 gives us minus 2.3 volts output. Here we have a graph of output versus input for a typical amplifier. Notice that there is a straight line portion of the curve and a nonlinear or curved portion on both ends. If you're operating in the linear portion, you have what's called Class A. In the curved portions, you have Class B or perhaps even Class C. If you're operating Class A, you will have great linearity, but your efficiency will only be 30%. That means that to get 100 watts out of your amplifier, you will have to be dissipating 300 watts. Here is an example of a Class B push-pull amplifier. Notice that each of these vacuum tubes is handling half of the input waveform signal. Amplifiers can easily become oscillators like a public address system that's squalling. Negative feedback can be used to reduce or eliminate unwanted feedback. Notice in this schematic diagram the variable capacitor connected between the output plate of the vacuum tube to the input grid. That's to improve stability and reduce the tendency to oscillate. Parasitic suppression can also be used to reduce oscillation at a particular frequency. Notice the parallel combination of the inductor and the resistor in the plate circuit of this vacuum tube. It's there to reduce the tendency to oscillate at a particular frequency. What is one way to prevent thermal runaway in a bipolar transistor amplifier? Is it A, neutralization, B, to select transistors with a high beta, or C, use a resistor in series with the emitter, or D, all of these choices? Answer C, use a resistor in series with the emitter. How can an RF power amplifier be neutralized? A, by increasing the driving power. B, by reducing the driving power. C, by feeding a 180-degree out-of-phase portion of the output back to the input. Or D, by feeding an in-phase component of the output back to the input. The answer is C, by feeding a 180-degree out-of-phase portion of the output back to the input. How does the gain of an ideal operational amplifier vary with frequency? A, it increases linearly with increasing frequency. Or B, it decreases linearly with increasing frequency. Or C, it decreases logarithmically with increased frequency. Or D, it does not vary with frequency. The answer is D, it does not vary with frequency.